Natural logarithm.
The natural logarithm of a number is its logarithm to the base e, where e is an irrational and transcendental constant approximately equal to 2.7182812828. The natural logarithm of x is generally written as ln x, loge x, or sometimes, if the base e is implicit, simply log x. Parentheses are sometimes added for clarity, giving ln, loge or log. This is done in particular when the argument to the logarithm is not a single symbol, to prevent ambiguity. The natural logarithm of x is the power to which e would have to be raised to equal x. For example, ln 7.5 is 2.0149. Because e 2.0149 equals 7.5. The natural log of e itself, ln e, is 1, because e1 equals e, while the natural logarithm of 1, ln 1, is 0, since e0 equals 1. The natural logarithm can be defined for any positive real number as the area under the curve y equals 1/x from 1 to a, the area being taken as negative when a less than 1. The simplicity of this definition, which is matched in many other formulas involving the natural logarithm, leads to the term natural. The definition of the natural logarithm can be extended to give logarithm values for negative numbers and for all non-zero complex numbers, although this leads to a multi-valued function, see complex logarithm. The natural logarithm function, if considered as a real-valued function of a real variable, is the inverse function of the exponential function, leading to the identities. Like all logarithms, the natural logarithm maps multiplication into addition. Thus, the logarithm function is an isomorphism from the group of positive real numbers under multiplication to the group of real numbers under addition, represented as a function. Logarithms can be defined to any positive base other than 1, not just e. However, logarithms and other bases differ only by a constant multiplier from the natural logarithm, and are usually defined in terms of the latter. For instance, the binary logarithm is just the natural logarithm divided by ln, 2, the natural logarithm of 2. Logarithms are useful for solving equations in which the unknown appears as the exponent of some other quantity. For example, logarithms are used to solve for the half-life, decay constant, or unknown time in exponential decay problems. They are important in many branches of mathematics and the sciences and are used in finance to solve problems involving compound interest.
History.
The first mention of the natural logarithm was by Nicholas Mercator in his work Logarithmotechnia published in 1668, although the mathematics teacher John Spadell had already in 1619 compiled a table of what in fact were effectively natural logarithms. It was formerly also called hyperbolic logarithm, as it corresponds to the area under a hyperbola. It is also sometimes referred to as the Napier'ian logarithm, named after John Napier, although Napier's original logarithms, from which Spadell's numbers were derived, were slightly different. See logarithm, from Napier to Euler.
Notational conventions.
The notations ln x and loge x both refer unambiguously to the natural logarithm of x. Log x without an explicit base may also refer to the natural logarithm. This usage is common in mathematics and some scientific contexts as well as in many programming languages. In some other contexts, however, log x can be used to denote the common, base 10, logarithm.
Origin of the term natural logarithm.
The graph of the natural logarithm function shown earlier on the right side of the page enables one to glean some of the basic characteristics which logarithms to any base one might wish to use have in common. Chief among them are, the logarithm of the number 1 is 0. And the logarithm of 0 is, in colloquial terms, minus infinity. What makes natural logarithms unique is to be found at the single point where all logarithms are 0, namely the logarithm of the number 1. At that specific point the slope of the curve of the graph of the natural logarithm also is precisely 1. Logarithms to a higher base than e, such as, for example, those to the base 10, exhibit a slope at that point less than 1, while logarithms to a lower base than e, such as, for example, Those to the base 2 exhibit a slope at that point greater than 1. While the methods for computing the value of E are fascinating from various mathematical perspectives, they all can be thought of as resulting from the pursuit of this condition. Another way of conceptualizing this is to realize that, for any numeric value close to the number 1, the natural logarithm can be mentally computed by subtracting the number 1 from the numeric value. For example, the natural logarithm of 1.01 is 0.01 to an accuracy better than 5 parts per thousand. With similar accuracy, one can assert that the natural logarithm of 0.99 is minus 0.01. The accuracy of this concept increases as one approaches the number 1 ever more closely, and reaches completeness of accuracy precisely there. To the same extent that the number 1 itself is a number common to all systems of counting, so also the natural logarithm is independent of all systems of counting. In the English language, the term adopted to encapsulate this concept is the word natural. Initially, it might seem that since the common numbering system is base 10, this base would be more natural than base E. But mathematically, the number 10 is not particularly significant. Its use culturally, as the basis for many societies' numbering systems, likely arises from humans' typical number of fingers. Other cultures have based their counting systems on such choices as 5, 8, 12, 20, and 60. Loge is a natural log because it automatically springs from, and appears so often in, mathematics. For example, consider the problem of differentiating a logarithmic function. If the base b equals e, then the derivative is simply 1/x, and at x equals 1 this derivative equals 1. Another sense in which the base e logarithm is the most natural is that it can be defined quite easily in terms of a simple integral or Taylor series, and this is not true of other logarithms. Further senses of this naturalness make no use of calculus. As an example, there are a number of simple series involving the natural logarithm. Pietro Mengoli and Nicholas Mercator called it logarithmus naturalis a few decades before Newton and Leibniz developed calculus.
Definitions.
Formally, ln a may be defined as the integral. This function is a logarithm because it satisfies the fundamental property of a logarithm. This can be demonstrated by splitting the integral that defines ln ab into two parts and then making the variable substitution x equals tar in the second part, as follows. The number e can then be defined as the unique real number as such that ln a equals 1. Alternatively, if the exponential function has been defined first, say by using an infinite series, the natural logarithm may be defined as its inverse function, that is, ln is that function such that exp, ln, x equals x. Since the range of the exponential function on real arguments is all positive real numbers, and since the exponential function is strictly increasing, this is well defined for all positive x.
Properties. Derivative, Taylor series.
The derivative of the natural logarithm is given by. This leads to the Taylor series for ln, 1 plus x, around 0. Also known as the Mercator series. Leonhard Euler nevertheless boldly applied this series to x equals -1, in order to show that the harmonic series equals the natural logarithm of 1 over opening round bracket 1 minus 1, that is the logarithm of infinity. Nowadays, more formally but perhaps less vividly, we prove that the harmonic series truncated at n is close to the logarithm of n, when n is large. At right is a picture of ln, 1 plus x, and some of its Taylor polynomials around 0. These approximations converge to the function only in the region 1 less than x. 1. Outside of this region the higher degree Taylor polynomials are worse approximations for the function. Substituting x. 1 for x, we obtain an alternative form for ln, x, itself, namely. By using the Euler transform on the Mercator series, one obtains the following, which is valid for any x with absolute value greater than 1. This series is similar to a BBP-type formula. Also note that as its own inverse function, So to yield the natural logarithm of a certain number y, simply put in for x.
The natural logarithm in integration.
The natural logarithm allows simple integration of functions of the form g, x, equals f, x, slash f, x. An antiderivative of g, x, is given by ln, f, x. This is the case because of the chain rule in the following fact. In other words, and. Here is an example in the case of g, x, equals tan, x. Letting f, x, equals cos, x, and f, x, equals sin, x. Where c is an arbitrary constant of integration. The natural logarithm can be integrated using integration by parts.
Numerical value.
To calculate the numerical value of the natural logarithm of a number, the Taylor series expansion can be rewritten as. To obtain a better rate of convergence, the following identity can be used. Provided that y equals x 1 slash x plus 1 and re x 0 but x 0. For ln x, where x greater than 1, the closer the value of x is to 1, the faster the rate of convergence. The identities associated with the logarithm can be leveraged to exploit this. Such techniques were used before calculators, by referring to numerical tables and performing manipulations such as those above.
Natural logarithm of 10.
The natural logarithm of 10, which has the decimal expansion 2.30258509, plays a role for example in the computation of natural logarithms of numbers represented in scientific notation, as a mantissa multiplied by a power of 10. This means that one can effectively calculate the logarithms of numbers with very large or very small magnitude using the logarithms of a relatively small set of decimals in the range.
High precision.
To compute the natural logarithm with many digits of precision, the Taylor series approach is not efficient since the convergence is slow. If x is near 1, an alternative is to use Newton's method to invert the exponential function, whose series converges more quickly. For an optimal function, the iteration simplifies to which has cubic convergence to ln x. Another alternative for extremely high precision calculation is the formula, where m denotes the arithmetic geometric mean of 1 and 4 per second, and with m chosen so that p bits of precision is attained. For most purposes, the value of 8 for m is sufficient. In fact, if this method is used, Newton inversion of the natural logarithm may conversely be used to calculate the exponential function efficiently. The constants ln2 and p can be pre-computed to the desired precision using any of several known quickly converging series.
Computational complexity.
The computational complexity of computing the natural logarithm, using the arithmetic geometric mean, is O, m, n, ln n. Here n is the number of digits of precision at which the natural logarithm is to be evaluated and m, n, is the computational complexity of multiplying two n-digit numbers.
Continued fractions.
While no simple continued fractions are available, several generalized continued fractions are, including. These continued fractions, particularly the last, converge rapidly for values close to 1. However, the natural logarithms of much larger numbers can easily be computed by repeatedly adding those of smaller numbers, with similarly rapid convergence. For example, since 2 equals 1.253x 1.024, the natural logarithm of 2 can be computed as. Furthermore, since 10 equals 1.2510x 1.0243, even the natural logarithm of 10 similarly can be computed as.
Complex logarithms.
The exponential function can be extended to a function which gives a complex number as x for any arbitrary complex number x. Simply use the infinite series with x complex. This exponential function can be inverted to form a complex logarithm that exhibits most of the properties of the ordinary logarithm. There are two difficulties involved: no x has x equals 0. And it turns out that e2 pi equals 1 equals e0. Since the multiplicative property still works for the complex exponential function, whose equals is plus 2n pi, for all complex z and integers n. So the logarithm cannot be defined for the whole complex plane, and even then it is multi-valued. Any complex logarithm can be changed into an equivalent logarithm by adding any integer multiple of 2 pi at will. The complex logarithm can only be single-valued on the cut plane. For example, ln I equals 1/2 pi or 5/2 pi or 3/2 pi, etc. And although I4 equals 1, for log I can be defined as 2 pi, or 10 pi or 6 pi, and so on.